Hello everyone, my name is Joong-Ku Lee from KAIST. Today, I will present a way to optimize setup configuration of a robot arm-based bimanual haptic display. Let me begin with the motivation of our research. The rapid advancement in metaverse and extended reality technologies have significantly increased the demand for sophisticated bimanual haptic displays, especially for applications like teleoperation, simulation, and learning of complex bimanual tasks. However, despite this technological advancement, current commercial haptic displays exhibit several limitations to be utilized as a bimanual haptic display. Most of the commercial haptic displays are typically desktop systems with limited workspace and insufficient force and torque feedback range. Although there are some devices that can cover the entire human arm workspace, they often demand a nearly room-sized space with high cost and complexity of setup. In response to these limitations, previous researchers have explored the potential of using collaborative robot arms as a haptic display. However, the setup configuration for this robot arm is often determined empirically, relying heavily on trier and error or user interface, rather than a systematic approach. As shown in this figure, the setup configuration can vary significantly, highlighting the need for a more structured and optimized solution. So several studies have attempted to address this challenge. Zacharias et al., for example, compared two configurations, a standard and an ergonomic setup, by defining reachability maps for both human and robot arms. However, their analysis was limited to just comparing two configurations and did not take into account critical factors such as haptic feedback or the potential for collision. Similarly, Lenz et al. Focused on maximizing the overlap between human and robot arm workspace. But again, they did not account for haptic feedback performance or collision. So, our research aims to overcome previous studies' limitations by considering multiple factors that are essential for haptic interaction or determining the optimal setup configuration of the robot arms. This includes to maximize workspace coverage, redundancy if the robot arm is redundant, maximize force and torque feedback rendering capability, and also considering potential collision between human and robot arm. Ultimately, we want this optimization method to be accessible and adaptable so that it can be applied to various off-the-shelf robot arms. Now, let's take a look at the design variables that form the basis of our optimization process. As shown in this figure, a slight variation of the robot arm base poses can lead to significant changes in the overall configuration of the robot arms. Given that this diverse set of configurations likely affect the performance of the haptic display, we have defined robot base position and orientation as design variables. Additionally, as depicted on the right side of the figure, various grab angles between robot end effector and the human palm are possible. We assume that this grab angle also has a significant impact on the performance of the haptic display and included this grab angle as an additional design variable for our optimization. And to simplify the optimization, we assume reflective symmetry between the left and right robot arms, including their base positions and grab angles. So, our optimization goal is set to find such set of configuration that meets these four key requirements. First, maximizing workspace because we aim to cover the widest range of human reachable poses, allowing unrestricted manipulation movement without disturbing the operator. Second, ensuring dexterity because maintaining redundancy in the robot arm's movement is essential to support fluid, natural human movements. Third, providing strong enough force feedback because the bimanual haptic display must deliver sufficient haptic feedback force and torque in all directions and under any circumstances to enable realistic haptic feedback. Last but not least, guaranteeing safety because it is essential to consider collision between the human and robot arms for optimization. I will show you the overview of our optimization process. We begin with the workspace discretization, dividing the workspace into discrete positions and orientations to generate Corey poses. Next, we check the human arm workspace using inverse kinematics to determine the human reachable poses from these discretized Corey poses. With this information, we move to the optimization phase, where we define a new set of configuration for the robot arms by adjusting the base positions, orientations, and grab angles. Then, we check the robot arm workspace to ensure the robot can reach to the human reachable poses. We then perform collision checking to check the possible collision between the robot arms and the human operator. Afterward, we evaluate the feedback force and torque rendering capability to confirm the robot can deliver adequate haptic feedback. Finally, we calculate the objective function, balancing workspace coverage, redundancy, and haptic feedback performance. This iterative process continues until we achieve an optimal configuration. The following sections will provide a detailed explanation of each individual step in the process. The first step is workspace discretization. Here, the workspace around the human operator is divided into discrete positions and orientations. The position is discretized using a fixed step size of 0.1 meters, while the orientation is uniformly divided into 50 orientations for each position. This discretization allows us to generate a set of Corey poses that can represent the operator's potential reach. Next, we assess the human arm workspace. For each Corey pose, we calculate inverse schematic solutions to determine the human's reachable poses. Since the human arm is a redundant system, there can be multiple inverse schematic solutions for each pose. Among these solutions, the most suitable human arm joint configuration for a given pose is determined by selecting the solution with the highest manipulability index. Using this information, we proceed to optimization phase. At this stage, our algorithm first defines a new set of configuration for the robot arms by adjusting their base positions, orientations, and grab angles. The new set of configuration candidates are generated using a particle swarm optimization algorithm. Once a new set of configuration is defined, we move on to check whether the robot arms can reach the human's reachable poses. If redundancy exists in the robot arm, multiple IK inverse schematic solutions may be available. However, if a specific human reachable pose cannot be reached by the human arm or robot arm, no inverse schematic solution will be found for that pose. An essential part of our optimization is ensuring safety. We perform collision checks between the robot arms and the human operator, including both the arms and body. As a result, the robot arm joint configurations that avoid potential collisions are identified. Following the collision check, we evaluate the robot arm's feedback force and torque rendering capability. The robot arms must compensate for both gravity and the human arm's weight, with the remaining torque allocated for delivering haptic feedback. Using singular value decomposition, we analyze the maximum torque exertion direction and determine the maximum renderable force and torque for each pose. Finally, we calculate the objective function, which is designed to balance both workspace coverage and haptic performance. The workspace-related component evaluates the robot arm's reachability and redundancy. On the other hand, the haptics-related component considers the rendering feedback force and torque. This ensures the optimized set of configuration achieves adequate haptic feedback performance and covers the widest range of human reachable poses. Now, let's look at our results. We initially tested our optimization method using Franca Amica Panda robot arm. Compared to previous approaches of Team Nimbro, our method achieved superior performance in most of the performance indexes. In another experiment, using KUKA LBR EVA 7 robot arm, our optimized set of configuration also outperformed the previously proposed DLR hog configuration. Here are some demonstration videos showing the real-world application with Franca Amica Panda robot arm. Our bimanual haptic display covers a majority of the human workspace, ensuring maximized redundancy and providing sufficient force-torque feedback capability. Optimized bimanual haptic display can be effectively applied to teleoperation tasks with its dexterity and sophisticated force-torque feedback capability. In conclusion, we have developed an optimization method for determining the optimal set of configuration of a bimanual haptic interface using collaborative robot arms. Our approach maximizes workspace coverage and force-torque feedback performance while ensuring collision safety. Our code is publicly available on GitHub, and we hope that this work will contribute to the development of similar haptic interfaces. Thank you for your attention.